Hey everyone, welcome back. I hope you're all doing well. In this video, we're going to learn about resource allocation, which is an important process for managing construction project resources. Resource allocation is a crucial challenge in project scheduling, as resources are often limited. When resources are set to a fixed limit due to availability and demand exceeds this limit, activities may need to be rescheduled to prevent over-allocation. For example, in a construction project with only one available crane, activities A and B may initially overlap, requiring 2 cranes at the same time. Since the resource limit is 1, activity B must be delayed to align with the availability of the crane. By strategically rescheduling activity B, the project can effectively prevent over-allocation while maintaining workflow efficiency. However, adjusting the schedule can have significant consequences. Extending or shifting activities to balance resource demand may lengthen the overall project duration. Additionally, these adjustments can alter the project's critical path, potentially creating new critical activities. To address over-allocation effectively, a structured method is needed. When resource over-allocation arises, involved activities should be ranked based on priority. Lower priority tasks can then be delayed to ensure that higher priority activities receive the necessary resources first. This approach helps maintain efficiency while minimizing disruptions to the project timeline. There are prioritization rules that can help you determine which activities receive resources first and which should be delayed. The main rules include: first, critical activities take priority over non-critical ones to minimize the impact on project duration. The second rule is based on the late start time. Those with the earliest late start should not be delayed. This helps minimize the risk of exceeding allowable float and prevent project delays. If multiple activities share the same late start, the one with the least total float takes priority to receive resources. If there's still a tie, the activity that requires the most resources will be prioritized. Let's apply these rules to prioritize the 4 activities in this example. First, we examine their late start times. Activity A has the latest late start, making it the lowest priority with a ranking of 4. Next, we compare the remaining activities. Since they have the same late start, we check their total float. Among them, activity C has the largest total float, meaning it has more scheduling flexibility. As a result, its priority is lower than activities B and D, giving it a ranking of 3. Now, we are left with activities B and D, which are tied in both late start and total float. In this case, we compare their resource requirements. Since activity D requires more resources, it has a higher priority. This means D is ranked 1, while B is ranked 2. Beyond these ranking rules, there are alternative ways to address over-allocation. One effective approach is to extend the duration of activities that have float, reducing the peak resource demand at any given time. For example, consider an activity initially scheduled to last 4 days with 4 workers assigned. The total workload for this task is calculated as 4 workers times 4 days, equaling 16 man-days. To lower the daily resource demand, we can extend the duration to 8 days. Since the total workload remains the same at 16 man-days, only 2 workers per day are needed to complete the task within this extended time frame. Another option is to reallocate resources within an activity to balance demand across different time periods. For instance, consider an activity originally scheduled for 4 days with 4 workers assigned. If the first 2 days experience over-allocation due to overlaps with other activities, we can adjust the resource distribution. Instead of keeping a constant workforce, we assign 2 workers for the first 2 days and increase the number to 6 workers for the remaining 2 days. This redistribution helps reduce the resource demand during peak periods while still maintaining the total workload of 16 man-days, ensuring the activity is completed on schedule without exceeding resource limits. If none of these adjustments resolve the over-allocation issue, critical activities may need to be examined. Since delaying critical activities directly affects the project completion date, careful consideration is required before making changes to them. Now, let's go through this example. Based on the initial resource plan and constraints, this is the schedule developed. The project manager requests you to resolve over-allocation issues, given a resource limit of 7 workers. First, you calculate the resource demand for each day along the project timeline and record it in a row below the schedule. For example, on day 1, 1 worker is needed for activity A, while on day 2, a total of 7 workers are required, 3 for B and 4 for C. Next, analyze the resource demand and identify over-allocation spots. In this case, days 5 and 6 exceed the resource limit with a demand of 8 workers, 3 for B and 5 for E, while the maximum available is 7. To resolve this, one activity must be delayed. Since B is critical, it takes priority, meaning E must be postponed by at least 2 days. This shifts its start to day 7 and completion to day 9. Now, recalculate the resource demand. On days 5 and 6, demand decreases by 5 as E is no longer scheduled. On day 7, demand remains unchanged since E was originally scheduled on that day. On days 8 and 9, demand increases by 5. due to E's new placement. Finally, update the resource usage row by adding these changes to the initial values. After adjusting E, the highest resource demand is now 7, resolving the overallocation and meeting the project's resource constraints. Alright, let's work through another example. Given the project details in the table below, your task is to reschedule the activities to ensure that the daily labor requirement does not exceed 6 workers. This table presents key scheduling information for project activities, including their duration, early and late start and finish times, float values, and labor requirements. From this table, we can easily identify the following critical activities, A, D, and F, as they have 0 total float. To address the overallocation issue, we first develop a resource-loaded early start bar chart, which visually represents how resources are allocated across the project timeline. Since we've already covered this process in a previous video, I'll skip explaining how we obtain this resource-loaded schedule. Now, we need to calculate the resource demand for each day. Using the same process as in the first example, here's the result. We identify overallocation on days 5 and 6, where 10 laborers are required while only 6 are available. During this period, activities C and D are running, requiring 4 laborers for C and 6 for D. Since D is a critical activity, it takes priority, meaning C must be delayed. To resolve the overallocation, we delay C by 4 days, shifting it later in the schedule. This adjustment makes C a critical activity, which we highlight in red. With this delay, the resource demand changes as follows. A reduction of 4 laborers on days 5 and 6, no change on days 7 and 8, and an increase of 4 laborers on days 9 and 10. After updating the resource usage chart, the first overallocated period is resolved. Next, we continue reviewing the updated schedule and notice another overallocation on day 9, where 7 laborers are needed, but only 6 are available. The demand comes from 3 activities running on that day. 1 laborer for E, 2 laborers for F, and 4 laborers for C. Since only E is non-critical, we first attempt to delay it. E can be delayed by 1 day without extending the project duration, but this alone does not fully resolve the overallocation, because the resource demand for day 10 will increase to 7. To fully resolve the issue, we now need to extend the project duration by 1 day, making the total duration 11 days. With this adjustment, activities E, F, and C all become non-critical, allowing more flexibility in scheduling. E has the lowest priority because it has the latest late start, the largest total float, and the lowest resource demand. Therefore, we delay E by 2 days, moving it to day 11. This change makes E critical, which we highlight in red. As a result of this adjustment, the resource demand decreases by 1 laborer on day 9 and increases by 1 on day 11. Incorporating these changes into the current resource demand, we now have the updated daily resource levels. As shown, we have successfully eliminated all overallocation, satisfying the resource constraint while minimizing project delays. Alright, that's it for this video, where we covered resource allocation methodology and illustrative examples. Thanks for watching, and we'll see you in the next video. Goodbye.